Video 6-3, metallic bonding, metallic properties, and we'll look at something called resonance structures. Okay, now, metallic bonding. Okay, well, pretty much you're going to find metallic bonding in metal. So, a metal bonded to a metal, metallic atom to a metallic atom. Okay, now, what happens in metals? Okay, the highest energy levels of metals have empty orbitals. Okay, only a few of those orbitals actually will contain electrons. Now, within a piece of metal, the vacant orbitals of one atom can actually start to overlap with the vacant orbitals from adjacent atoms right next to them. Okay, and because the difference in energy levels between where the electrons are and the empty ones is small, the valence electrons can actually jump up from where they are to the overlapping orbitals. In other words, you may have electrons in these orbitals like this in a piece of metal, okay, and the metal right next to it may have the same type of electrons and the same types of orbitals. Okay, the orbitals right above them are empty. Now these can overlap. So these electrons can jump up here. These electrons in this atom can jump up here. And once they're up here, they're free to move from one atom to the next atom to the next atom. Okay, electrons are free to roam throughout the entire metal when they're in these overlapping orbitals. Okay, and now these electrons are known as delocalized electrons. Okay, localized electrons, basically, the electrons are confined around the nucleus. Okay, so these would be localized electrons. So here's another atom. These electrons can't jump from one to the others because these would be localized. Okay, now, this creates, when you have delocalized electrons, something known as a sea of electrons. Okay, and the metallic bond does not result because these electrons, if they would overlap and overlap, okay, it's not because of the overlap that causes the bond. It's because when the electrons jump up to here and jump up to here, the nucleus attracts its own electrons plus the electrons from the adjacent atom. Okay, and so does this nucleus. Does the same thing, attracts its own electrons plus the ones that are in the sea of electrons. Okay, so think of each atom here as an individual building. Okay, and the nucleus is going to be down here someplace. Okay, so this is one atom, this is another atom, this is another atom, this is another atom. Okay, and these are all metallic atoms. Okay, so let's say you got electrons in this floor, electrons in this floor, but the top floor is empty. Electrons here, same thing. Okay, now the top floors are empty, but they overlap like this. Okay, so these electrons are free to jump up here. These can jump up here, these can jump up here, these can jump up here because to get from this floor to this floor, it's a real small gap. Now, once they're up here, they can go anywhere they want to. Okay, and it's not this movement that causes this atom to be bonded to this atom. It's because this attracts its own electrons, plus it's attracting the electrons here. Same thing here. This is attracting its own electrons plus the ones that are up here. Okay, so it's this attraction by each nucleus to the sea of electrons that holds them all together. Okay, so basically what happens now, the electrons in the top energy level actually are no longer confined around this individual atom. So these basically leave. So the atoms in a metal are actually cations surrounded by the valence electrons that are free to move. Okay, so a lot of times when they talk about metals being bonded together, they don't say they're actually metals. We actually call them cations, surrounded by the sea of electrons, and each nucleus attracts the electrons in the sea of ions. Okay, now these are good conductors of heat and electricity. Okay, let's go back. Why is it a good conductor of heat? Heat energy basically causes the molecules to move faster, and When these start to move, they vibrate, they hit the next one. This vibrates, hits the next one, vibrates, hits the next one. Okay? And because the molecules are pretty close together, it lets the heat travel relatively well. Okay? Good conductors of electricity, because remember, in order for electricity to flow, you need a movement of charged particles. Okay? And the electrons in the sea of electrons are free to move. So electricity flows really well through metals also. Okay? The shiny appearance, okay? The metallic luster due to the excitation of electrons by light. In other words, from what you know, electrons are in the ground state, light hits them, they jump up to a higher energy level, they don't stay there, they fall back down again, and then they shoot off photons. Okay? They're malleable. Okay? Now, why are they malleable? And why are they ductile? Let's go back, take a look. Okay. Well, if you apply a pressure, even though these are cations, because you still have the electrons in between, the cations never really get closer to the cations. And these, even as they move, they're still attracted to the sea of electrons. Okay. So it's pretty easy for them to move, but not break apart. Okay. Now, the strength of the metallic bond can be measured by something known as the heat of vaporization. Okay. Now, all metals have different heats of vaporization. And this is basically the amount that you need, amount of heat that you have to add to vaporize the metal. Okay. So in other words, take your metal in the solid phase, add heat to it, and it will turn into the metal in the liquid phase. Okay. And this amount of heat that you have to add, this is the heat of vaporization. Okay. Now, resonance structures. This goes back to your Lewis or electron dot structures. Okay. Some molecules and ions can be represented by more than one Lewis structure. Okay. And the example, O3. O3 is ozone. Okay. Now, what is ozone? Okay. Well, we draw our structures. Remember, every oxygen has 6 valence electrons. Okay. So they have to share 2. Now, if the middle one shares 1 on the left and 1 on the right, the oxygens on the left and the right only end up with 7. So what happens? It shares 2 with one of those. This has 4 remaining, so you still have your 6 plus the other 2 gives you 8. Okay. Now this one ends up looking like that. So this has 2, 4, 6, 8. Okay. Now, how do you bond to the other one? Well, get rid of those 2 and turn them into a coordinate covalent bond. And then this one here doesn't share any, so it has 6. Okay. Now, is that the only way you can draw it? No. You can move the double bond to the other side. So the other structure, the way you can draw ozone is like this. Put the double bond here, share 2 that way. The arrow goes this way. You still have 1 more pair. Okay, now resonance structures. The atoms have to be in the exact same spot. So this is atom number 1, this is atom number 2, this is atom number 3. This is still the exact same atom, 1, 2, 3. Okay. Now why are they different? Because in 1 and 2 in this structure, you have a double bond. Here between atom 1 and 2, you have a single bond. So that makes them different structures. Okay. 2 different structures that represent the same structure, these are known as resonance structures. Okay. And you show that they're the same structure, but resonance structures of each other by using a double arrow between them. Okay. Now, what's the actual structure? Is this the correct one? Is this the correct one? Okay, well, if either one of these was correct, they can actually measure the bond distance between atom 1 and 2 and between 2 and 3. Okay, and regardless of which one you pick, you should see a double bond distance and a single bond. Double bonds are shorter than single bonds. Okay, and no matter which structure you're looking at, you would expect them to find that there should be a long bond and a short bond. Turns out that when they measure it, the bond between 1 and 2 is exactly the same length as the bond between 2 and 3. Okay, so what's the correct structure? It's actually the average of the structures. The bond length turns out to be about a bond and a half distance. Okay, use the double arrows to represent the resonance structures. Okay, now, if a substance has an odd number of valence electrons, add up all the valence electrons in the compound. Okay, it's going to be stable, but the only reason why it's stable is because multiple resonance structures can be drawn. Okay, and none of them will have complete octets. Okay, none of the resonance structures are you going to be able to put complete octets around every single atom. It's mathematically impossible. Okay, now, when can you usually draw resonance structures? Okay, well, if you have a double bond and a single bond, usually you can draw resonance structures simply by just moving the double bond around. So for the review, what is the difference between a localized electron and a delocalized electron?